This is number 57 in chapter 14. It looks at calculating equilibrium concentrations from initial concentrations and an equilibrium constant. And so to begin, we have to consider the following reaction. So we have Br2 and Cl2 in equilibrium with BrCl. These are all gaseous. They give us an equilibrium constant with regards to pressure to be equal to 1.11 times 10 to the negative fourth. And this was at 150 Kelvin. They tell us the pressure of our Br2 initial is equal to 755 torr. They say the pressure of our Cl2 initial is equal to 735 torr. What is the pressure of BrCl at equilibrium? So we're given some initial pressures. We're given an equilibrium constant at a temperature, and we want to figure out what the equilibrium pressure would be for our product. And so we first should write what our equilibrium constant is going to be equal to. And so that equilibrium constant would be equal to the pressure of our BrCl squared over our pressure of our Br2 times the pressure of our Cl2. And so from that we need to construct our ice table. We have, these are pressures, the pressure of Br2, the pressure of Cl2, and the pressure of BrCl. We have an initial, a change, and an equilibrium. And so initial, we have 755 torr for Br2, 735 torr for Cl2, and 0 torr for our BrCl. There's going to be a change that's going to occur. Minus x for our starting materials, plus 2x for our product, again because of that stoichiometry. And then at equilibrium, we have 755 minus x for our Br2 pressure, 735 minus x for our Cl2 pressure, and 2x for our BrCl. So if we now take these values and plug them into our equilibrium expression, we would end up with 2x squared over the quantity 755 minus x times 735 minus x. So we took our initial set of pressures, we looked at the change, and now we substituted in what would happen at equilibrium as a result of that change. We then substituted those equilibrium expressions into the actual equilibrium equation. And so what we need to do now, in order to figure out the pressure of BrCl, we have to figure out what x actually is. So I'm going to leave the table, but I'm going to come up to the top of the board here and begin again. So right now we have our 1.11 times 10 to the negative fourth equal to the quantity 2x squared over 755 minus x times 735 minus x. And so we have a problem here because we're going to get, if we multiply these two guys through, we're going to get an x squared quantity as well as an x. We also have an x squared quantity in the numerator, and things can get kind of confusing. What we want to do here is make an assumption, and the assumption is as follows. Since our k is less than or equal to 10 to the negative fourth, that means that change, or X, will be small. For starting materials that have an initial pressure or concentration. And so in this case we have initial pressures. So since we're starting with a large concentration or large pressure of our starting materials, Br2 and Cl2, and since our equilibrium constant is so small, it's less than 1, that means that our starting materials are really favored in this equilibrium. If our starting materials are favored, then that means that this X quantity is going to be really negligible compared to those initial concentrations. And so as a result, our equilibrium simplifies, meaning that this equilibrium constant is going to be equal to still the 2x squared in the numerator, but in the denominator we are getting rid of the x value. Again, the reason is because we have a large pressure for our starting materials and our equilibrium constant is really small, which means our starting materials are favored. If our starting materials are favored, that means that the change is going to be very small compared to that initial pressure, and as a result we can assume it's negligible. And so now if we work this equation, we would get 1.11 times 10 to the negative fourth is equal to 4x squared over 554,925, the product of 755 and 735, and if we continue to do some math, we should get our x squared equal to 61.59 over 4, which is equal to 15.399. So that's where we're at now. We have that x squared value. That's where I'm going to begin here. I'm going to make some room. And so we have now at this point our x squared equal to that 15.399. And so that means x would be equal to the square root of the 15.399 to give us a value of 3.924, and that would be in terms of pressure or torr. So that is our x value, 3.924 torr. And if we're trying to determine that pressure of BRCL, remember that that is equal to 2x. So our pressure of BRCL would equal to 2 times 3.924, or be equal to 7.848 torr. And that is our answer. Now, one thing we have to be careful of is when we make an assumption like we did in this question, we have to make sure that that assumption is valid. We have to make sure that what we assumed, which was that the change x would be really small compared, or negligible compared to those initial pressures, that assumption we have to check to make sure it's valid. So in order to check the assumption, we're just simply going to take a percentage. We'll take x over our initial pressure times 100. And we want that to be less than or equal to 5%. If it's less than or equal to 5%, that means we have a good assumption in that the change is going to be very small relative to that starting material, and we can simply drop it out of the equation as we did. And so if we take our X, 3.924, I'll divide it by the smaller of the two pressures, the 735. We times that by 100, and we get 0.5%. That means that that is a good assumption, and we can go on with being confident that our value of 7.8 torr is correct for the equilibrium pressure of BRCL. That is number 57.